So welcome to another video on chemistry revision. We're revising paper 1 and the topic everyone struggles with, quantitative chemistry, the maths in chemistry, calculating moles. We're going to look at what moles are, we're going to look at what the limiting reactants are, we're going to look at what atom economy is. All of these things, people see this maths question come up in their chemistry paper and they're like, oh my god, I can't do this, they don't understand it. But after this hour, you will be able to understand it. There's two formulas in this video that you really need to remember. It's essential that you remember, and then I have a method that I'll talk you through that can solve pretty much any question that the examiners will throw at you. So I'm not going to go through the advanced exam info because nothing from this topic has been taken out completely for anyone, which is daunting, maybe, perhaps. But there are a lot of bits in here for higher tier only, so if you're doing foundation, all I can say is lucky you. And there's also quite a few bits for triple science higher only, which is what I call chemistry as a separate science course. Yeah, triple science. So let's get into the video. So before we get stuck into moles and limiting reactants and everything, we're going to have a simple look at mass in equations. You need to understand this stuff before we move on to the harder stuff. So pause and have a go at these 11 questions. So the law of the conservation of mass simply states that the mass of the reactants in a chemical reaction is equal to the mass of the products of a chemical reaction. That's simply stating that no atoms are created or destroyed in chemical reactions. That's something you should know. Basically means that the same amount of atoms are there in the reactants as there are in the products. So in the last video on bonding, we discussed a lot about this little 2 here. We talked about how it referred to in the covalently bonded molecule of water, H2O, there are 2 hydrogen atoms and 1 oxygen atom covalently bonded together. But the big 2, it simply refers to the ratio of molecules that we need in that chemical reaction. So if you remember, when we balance chemical equations, we put 2's in front of some of them. We're simply finding the ratios of different molecules that we need so that we have the right amount of atoms to keep the mass equal on both sides, because otherwise only some of the reactants will react together and it will be the limiting factor. Again, I'll show you an example. So here we have a simple equation showing lithium and fluorine bonding together to form the simple ionic compound lithium fluoride. As we can see, this doesn't really follow the conservation of mass, does it? Because on this side we have, we have 1 lithium, 2 fluorines. This side we only have 1 fluorine. So this means that we need 2 lithiums because the fluorines come in pairs because they're diatomic covalently bonded, as we covered in the previous videos. So to balance, we put a big 2 in front of the lithium, and it simply means like the ratio of lithium molecules to fluorine molecules is 2 to 1 because fluorine atoms come in pairs. That's basically just what the big 2 means. So we would sometimes observe a decrease in mass. Say our chemical reaction produced a gas, and the vessel that we did the chemical reaction in wasn't sealed, then the gas would just escape out, and we would observe a change in mass. In reality, the mass of the products produced would be exactly the same as the mass of reactants used, but because that gas would escape, we wouldn't detect that gas when we weighed our products, and we would detect a change in mass in our products. Similarly, an observable increase of mass may happen when one of our reactants is a gas. So I'll give you an example. When iron rusts to turn into iron oxide, for example, if we weigh the iron and then the iron oxide, it appears the mass has increased, but no, we've just added oxygen from the air that's come in and reacted with the iron. But our weighing of the reactants doesn't take into account the oxygen that's in the air. And the mass change, the specification says you need to know it in terms of the particle model. Well, let's take our decrease, for example. Our product produces a gas. We know that in the particle model, gases expand to fit the available space, so it expands and leave the vessel, because you've got to imagine all those molecules in the gas, they're all moving, aren't they? So they would just move out and away. They wouldn't stay fixed, weighted down on the floor by the bonds between them. Okay, now we're going to get on to a really important bit to understanding this topic: relative formula mass. The relative formula mass, it's simply just it's of a molecule, so we add all the relative atomic masses of the atoms in the molecule together to form the relative formula mass. Take H2O, for example. Do you remember what relative atomic mass is? It's kind of that average mass of taking into account all the isotopes of an element. So we add up the relative atomic mass of each of the elements to get the relative mass of the molecule, and we call that the relative formula mass. So the relative formula mass of water, well, the relative atomic mass of oxygen is 16, the relative atomic mass of hydrogen is 1, but we have 2 hydrogens, so it'd be 2 plus 16 is 18, and if we were finding the relative formula mass of 2 H2Os, it would be 36. I link back to what we've just done with conservation of mass. If the relative formula mass of the product of a reaction is 62, the relative formula mass of the reactants of a reaction would also be 62, because no atoms are created or destroyed during the reaction. So the relative formula mass of lithium oxide, first we're going to have to find the empirical formula of lithium oxide. If you don't know what that is, go back, have a look at the last video. Again, this is drawing on a lot of the key concepts from last video, because lithium oxide is between a metal and a non-metal, so it's an ionic compound, so we have to kind of work it out, don't we? So lithium is in group 1, so it has 1 electron to give, and oxygen is in group 6, so it has 2 spaces for electrons. So if we bonded 1 lithium and 1 oxygen, it wouldn't work, because the oxygen's outer shell wouldn't be filled up. So we need 2 lithiums to provide 2 electrons to satisfy the oxygen. So the empirical formula of lithium oxide is Li2O, because we need 2 lithiums for every oxygen. So if you haven't already got a periodic table out, I really would recommend you do, because you do need to know the relative atomic masses of all the elements, and you can find that on the periodic table that you'll get in the exam. The relative atomic mass of lithium is 7, and we have 2 lithiums, so we times it by 2, and then we add on 1 oxygen, and oxygen is 16, and that's 14 plus 16, and that's 30. So the relative formula mass of lithium oxide is 30. So I hope you kind of followed what I did. The actual process of calculating the relative formula mass, this bit's it's the same every time, but this bit over here, that was entirely from the last video. I just thought I'd chuck it in there to make sure that you understood that as well, because all of chemistry links together, and that's kind of why none of the content has really been said that it's not going to be in the exam, because pretty much everything is going to be tested at some point. So calculating the percentage mass of an atom in a molecule or a compound, it's actually quite easy. First of all, you're going to need the relative atomic mass of each atom. So carbon is 12 and hydrogen is 1, but we got 4 hydrogens, so it's going to be 4. So the relative formula mass of methane, and again you do need to know that methane is 1 carbon and 4 hydrogens. We covered that in the last video. So the relative formula mass of methane is 16. So what is the percentage mass of hydrogen in methane? Well, hydrogen makes up 4 out of the total 16 of methane's relative mass. So 4 out of 16 is 0.25, which is 25%. So that's just how you work out the percentage mass. You take the relative formula mass as the denominator, and the relative mass of the atom that you're trying to figure out as the numerator, and we get our final answer of 25%. So here's a more complicated way that they could ask about the percentage mass in the exam, what it's essentially asking is how many grams of ammonia would you need where 20 grams of that ammonia is made up of hydrogen. So we need the percentage mass of hydrogen in ammonia. From the last video, again, you should know that ammonia is NH3. That's an important thing to know throughout both chemistry papers as it comes up quite a bit. And the relative mass of free hydrogens is 3 because the relative atomic mass of one hydrogen is 1, and the relative formula mass of ammonia is 17 because nitrogen is 14 and free hydrogens are 3, and that is going to equal an awful number. So, but what we can do is we can leave it as a fraction and we can kind of make an equation with it, because if we say the amount in grams of ammonia is x, okay, and 3/17 of this amount in grams is 20 grams, because 3/17 of ammonia is hydrogen and 3/17 of our amount of ammonia is 20 grams. So what we can do is then we can times by 17 to get 3x is equal to 340, and then you can divide by 3 to get x is 113.3 recurring. That's a question with quite nasty numbers. They're likely to give you easier numbers in the exam. So that's simply how you do it. In this section, you do need to know your maths, okay? You need to be able to rearrange formulas. Some people find it easier to use equations for maths. You might just find it easier to do it a different way. That's up to you, but this is how I've shown you to do it. You could also do it as a ratio. So if we know that 3/17 is 20, we can work out 1/17 to be 6.6 recurring, and then times that by 17 to get your answer. You do it as a ratio like that. So the specification does state that you need to be able to calculate the uncertainty. That is a general scientific calculation you need to be able to do. So I've got an example. Say we've done an experiment, you repeat it 3 times to be scientifically accurate, and the question asks you to find the uncertainty of the mean. So our first experiment gave us the result of 6, our second experiment gave us the result of 7, and the third experiment gave us a result of 8. So to calculate the mean, first of all, because it's the uncertainty of the mean, so we need to know the mean first. 6 plus 7 plus 8 is 21. 21 divided by 3 is 7. And as I've written here, the uncertainty is simply the range divided by 2. So the range, we have 8 minus 6, 2. The results range over 2. So 2 divided by 2 is 1. So we have an uncertainty of 1, and we get, we'd write it like this with the plus minus symbol. It simply just means like plus or minus, give or take. 7 give or take 1. It represents the uncertainty because like 7 plus 1 is 8, 7 minus 1 is 6. Again, you'll have more complicated numbers in the exam, but that's just a brief overview of how to calculate it. So now we're going to introduce moles, the thing that everyone seems to struggle with. This is for higher tier only, so if you're foundation tier, lucky you, you can skip to the next non-higher tier bit, which I'm not sure where that even is, because a lot of the more complicated calculations are higher tier only because they are, well, to be fair, actually they're not that complicated. But pause the video, have a go at these 8. So a mole, it's simply what we use in chemistry to measure the amount of a substance. We say we have X amount of moles of a substance. And the next 3 questions illustrate what 1 mole is. So Avogadro's constant is simply 6.02 times 10 to the 23. That is Avogadro's constant. Remember that number, 6.02 times 10 to the 23. That's in standard form. And that is how many atoms or molecules or whatever are in 1 mole of a substance. So if I have 1 mole of oxygen, there are 6.02 times 10 to the 23 atoms of oxygen in that mole. If I have 1 mole of uranium, there are 6.02 times 10 to the 23 atoms of uranium in that mole. There's another special thing about moles. 1 mole of a substance is equal to its relative mass in grams. So if I have 1 mole of oxygen, again, I have 16 grams of oxygen because the relative atomic mass of oxygen is 16. Let's try it with carbon dioxide. Its relative formula mass is 12 plus 2 16s, which is 44. So if it has a relative formula mass of 44, then 1 mole of carbon dioxide will be 44 grams, and again there will be 6.02 times 10 to the 23 molecules of carbon dioxide in that mole. That is essentially what a mole is. Okay, now the equation for moles. This, you have to remember, this equation you need to use in almost every calculation in chemistry. You don't get an equations sheet in chemistry, so you really need to remember this. Moles, the number of moles of something you have is equal to the mass in grams of that substance divided by the relative formula mass of that substance. So let's try it with methane. I have 80 grams of methane. How many moles of methane do I have? What is the relative formula mass of methane? Well, we have 1 carbon, which is 12, and 4 hydrogens, which are 1, so that'd be 16. So applying the equation, mass divided by formula mass. Remember that, mass divided by formula mass. So mass, 80 grams, divided by formula mass, 16. So if I have 80 grams of methane, I have 80 divided by, I have 5 moles of methane, because I've done 80 divided by 16. So 1 mole of methane is 16 grams, because that's its relative formula mass. And in 80 grams of methane, I have 5 moles, and that'd be 5 times 6.02 times 10 to the 23 molecules of methane. Okay, so question 6, balance this equation. Balancing equations is so important in chemistry. These should be little 2's, but on paint I can't make them to be little 2's. Don't draw them as big 2's in your exam. The examiners hate it because the big letters, as we mentioned earlier, go at the front. They also represent how many moles, we call it the mole ratio, because as I said, moles are just a measure of the amount of substance. So let's balance it first before I explain that. So we have 1 of each atom on this side, and on this side we have 1 of this, 2 hydrogen and 2 chlorine. Again, we need to balance it because we can't create or destroy any atoms according to the law of conservation of mass. We need the same amount of atoms on both sides. So we need to get from 1 to 2 of both of these, and the very convenient way to do that is just to stick a 2 in front of there, and that makes 2 of each, and we've balanced it. Now, as I was saying about how this is like a mole ratio, that's like saying for every 1 mole of magnesium I have, I need 2 moles of hydrochloric acid, because moles, again, they're just a measure of the amount of a substance. So, question 7, I used 335.8 grams of hydrochloric acid in the reaction. Assuming hydrochloric acid is the limiting reactant. We'll get onto what this means later, but it's essentially just saying assume all of it is used up. How much magnesium chloride was produced? So this is very much a more complicated, higher tier question. So what I really recommend is kind of almost making a table with it. So you write out mass, relative formula mass. This is how we symbolize it, the moles and the moles that we actually have, and the mole ratio in the equation, because we can find all of these out using our one equation, moles equals mass divided by formula mass. So first of all, we're going to fill in what we know. So as you can see, I've calculated the relative formula mass. Remember, we don't take into account the mole ratio, just the relative formula mass. Chlorine is 35.5, hydrogen is 1. And then I've calculated the amount of moles we have in 333.5.8 grams of hydrochloric acid, because mass divided by relative formula mass gives you the moles, so that divided by that is 9.2. And then I filled in our mole ratio, and you simply get that from the chemical reaction. If there's nothing in front of it, it's simply a 1, but if there is something in front of it, it means for every 1 mole of this, there's that number of moles of that. So there's a couple of ways of solving it. The tricky way is you could find the percentage mass of hydrogen in hydrochloric acid to find out the mass of hydrogen atoms we have, and then find out the mass of hydrogen that would be produced on the principle of the law of conservation of mass, because the same amount of hydrogen atoms that went in would come out. But we have the moles and the mole ratio. So because we have this, we can calculate the number of moles of every other element, element or compound that we have. So we need kind of our decimal multiplier, if you will, to get between the mole ratio and the moles, because it is in a ratio. So 2 times 4.6 comes out to be 9.2. So we have 4.6 times the mole ratio. So because it's a ratio, we do the same thing to everything. Same thing to everything, same thing to every number. So times 4.6 to all the ones, they'll all come out to be 4.6. So now we've actually come very, very close to finishing our table. We're just going to refer back to the question it asked: what is the mass of our magnesium chloride produced? So again, we can use our one single life-saving equation. Moles is mass divided by relative formula mass. We've got to rearrange it to find out that moles times relative formula mass equals the mass. So if we multiply these two together, we find out that if we put in 335.8 grams of hydrochloric acid, we're going to get out 437 grams of magnesium chloride. I wanted to show you this question because it's specifically hard, but I wanted to show you this method because it relies entirely on one formula, moles is mass divided by formula mass, and being able to rearrange it, and the fact that we can use our mole ratio from the balanced symbol equation to calculate the number of moles. You can use this in anything. There's a lot of questions are simply going to be this, and it turns even the most complicated of questions into just doing this, and it's actually just a series of calculations that you can put into your calculator. For me, the only tricky bit is figuring out whether you have to use this 2 or not. 99% of cases, no. You just find the relative formula mass of this, not including the 2, so this isn't 73. This is just referencing the mole ratio, not the relative. It's not going to be part of the relative formula mass of this. However, the little 2's, or what should be little 2's, but they're actually big 2's, they do count because one molecule of hydrogen, because hydrogen's diatomic, you would have 2 hydrogens bonded together, which would give you a relative formula mass of 2. And again, ionic compounds, look at the last video if you're unsure why, but we need 2 chlorines for every 1 magnesium. So we do have to do 2 chlorines in our relative formula mass. But this is just the mole ratio. This means for every one of it we have 2. It doesn't mean that we have to do 2 for the relative formula mass, if you understand. So if to practice this, because I understand it might seem quite confusing, practice it, find questions on it, and just practice drawing out this table with the 4 things here and calculating all the values for everything. Because trust me, after a few tries it's going to be very, very easy, and you're going to be able to get 6-mark calculation questions. You're going to find them a breeze. So here's actually another example. So this time we want to write a balanced symbol equation for the reaction between nitrogen and I should say hydrogen there, to produce ammonia. So we're looking for the mole ratio because that's essentially what the numbers on the outside that balance the symbol equation are. First of all, though, we need to write our symbol equation. So what's nitrogen going to be? Well, be careful. Again, coming from the last video, check. Is it a metal or a non-metal? Nitrogen is a non-metal from group 6. So it is diatomic. So it's N2. And hydrogen, I know it doesn't say it there, but it should say it. Hydrogen, again, hydrogen is a non-metal, so it's diatomic, and it's not from group. If it's a non-metal in group not from group 8, then you can assume it's diatomic. And ammonia, again, you need to know is NH3. So We've started the table again. As I say, that you can use the table for everything involving mass, relative formula mass, and moles. So at this point, we could go through and we could balance it like we usually do, but they could, I don't know if they will, but they could give you a question that asks you specifically to balance an equation by considering the moles and to show how you do it. So again, the table, this is much, much easier than the last question. We simply have to find the number of moles we have of each of the compounds, molecules, whatever. So again, for everyone, mass divided by relative formula mass, and you get these. Now, the mole ratio, we're simply looking at expressing these in a ratio. So you can look at the relationship between the numbers. So 24 times 2 is 48, 24 times 3 is 72. But there's a small trick you can do. You can divide all of the moles by the smallest number of moles you have. So 0.24 divided by 0.24 is 1, 0.24 divided by 0.72 is 3, and 0.24 divided by 0.4, well, sorry, no, I'm saying it the wrong way around. 0.48 divided by 0.24 comes out to be 2. And this is kind of our mole ratio, as you can see, because we have this times 3, and this times 3, and this times... yeah, never mind. But what we can now see is we can now balance it because we have 3 of these and 2 of these. This is our mole ratio, and as you can see, it works because on both sides we have 2 nitrogens, and on both sides we have 6 hydrogens. So remember this table. This is what I recommend to you. It's going to make it so much less complicated. And remember the formula. If you forget the formula, just don't forget the formula. Don't forget the formula. So obviously in real life, not all the time are we going to react the perfect amount with the perfect amount. So we're not always going to take exactly 6.72 grams of whatever it was, nitrogen, with 1.44 grams of hydrogen exactly, are we? There's going to be different masses that we take, and that gives us a limiting reactant. The limiting reactant is the reactant that's used up. It's the reactant that we have least of in our ratio. So while one of our reactants may be used up as the limiting reactant, some of the other will be left over if we have an excess of it. So the quantity of limiting reactant is directly proportional to the quantity that we get out of everything else, if that makes any sense, because you have to think, if we have, say we did have 6.72 grams of nitrogen, but we had 12 grams of hydrogen, if we put it together, this amount will only mean that 1.44 grams of hydrogen is used. The other 10.56 grams that's not going to be used at all. That's just going to be left over in excess. So the mass of the limiting reactant will be directly what we use to figure out the moles and mole ratio and all of that stuff. So this question is quite simple, really. You just have to figure out the main problem is you have to figure out what the chemical equation is, and therefore what the limiting reactant is. The combustion of methane, when we combust something, we just react it with oxygen, so it's going to be methane plus oxygen forms carbon dioxide plus water. Because we have so much oxygen in the air, methane is obviously going to be the limiting reactant, so 32 grams of methane will be burnt, and we know that the amount of oxygen isn't going to affect that. So once we've written out our symbol equation and balanced it, the tricky bits here, remembering that oxygen is diatomic, and balancing is quite easy because you can see we need 2 more hydrogens, so we're going to add 2 more onto here to make 4 hydrogens on either side, and then you can see that we've got 4 oxygens on this side but only 2 on this side, so we'll add a 2 on this side to make 4 oxygens. Practice, have a go, see if you can fill in this table on your own and figure out the mass of carbon dioxide that's going to be produced. So how you'd start it, you've got 32 grams of methane, you can figure out the relative formula mass to be 16, and therefore we know that if we have 32 grams of methane, we have 2 moles of methane. And again, we can use our mole ratio because we know that for every mole of methane, we need 2 moles of oxygen. So for every 2 moles of methane, we're going to have 4 moles. Again, you can visualize this just by multiplying. You multiply everything equally. So for every 1 mole of methane, 1 mole of carbon dioxide is going to be produced. So for every 2 moles of methane, there's going to be 2 moles of carbon dioxide. The relative formula mass of carbon dioxide is 44, and therefore we can multiply them together using our equation, remember, to figure out the mass of this produced is going to be 88. Again, we didn't really have to use the idea of a limiting reactant too much. We just had to remember that this would not be the limiting reactant because we have a huge abundance of this, but this would be the limiting reactant. Because if we added more, then we could produce more stuff because there would be more oxygen available. So that's just an illustration, if you will, of what the limiting reactant is. So here is kind of a harder question on how it might come up. I want you to go and see if you can have a go at this yourself. Remember, draw out your table of the mass, the relative formula mass, moles and mole ratio. You've got the balance symbol equation already. You have some of your masses, and it's also given you the relative atomic masses in the question, so you don't have to go and look at your periodic table. So yeah, have a go at this one and see how far you get. See if you can show that aluminium is the limiting reactant, because this is iron oxide, by the way. Okay, so hopefully you should have been able to get this far. We have obviously the table here. Mass, remembering grams, not kilograms. You need to convert it into grams, which isn't too hard because they're pretty simple numbers. And the mole ratio we've got, for this question, I don't even think the products actually matter. And then I've worked out the relative formula mass of each one. Aluminium is 27 and iron oxide is 160. So now we need to work out the moles. Let's start with iron oxide because we know that it is not the limiting reactant. And we have 18.75 moles of iron oxide. So we could actually use this to predict the amount of aluminium we should have. So if we times that by 2, then we get 37.5. So we should, if these two are equal, we should get 37.5 moles, because that's how many moles of aluminium oxide we need to react with 18.75 moles of iron oxide. But if you plug these values into the formula, then we get a 37.037. So we have less of this than we need to react with this. So you write a sentence, so say something like, we need 37.5 moles of aluminium to react with 18.75 moles of iron oxide. However, we only have 37.037 recurring moles of aluminium oxide, which is less than what we need. So therefore, while the aluminium will be used up fully, it is the limiting reactant, and at the end of the reaction there will be some iron oxide left in excess. And there we have it, complicated exam question, 4-mark calculation, solved pretty easily by the table. There are other ways of doing it, but I like the table just because it's obvious to see what you're doing, and you use it for all the other moles and mass stuff as well. So we've actually made it past probably the hardest bit, like all of the moles stuff. We've made it past that. We're on to concentration now. We got 7 nice, easy concentration questions, and for anyone doing triple science higher, we've got 5 hard, nasty questions on concentration, but more complicated. So pause the video, have a go at these 7 or these 12 if you're triple science higher. So, concentration is a measure of the amount of a solute dissolved in a given volume of solution. We measure concentration in grams per decimeter cubed. So grams being the mass of the solute and decimeters cubed being how we measure volume. Remember, 1 decimeter is 10 centimeters. Again, we'll cover question 6. Let's answer question 6. Why not? But because it's cubed, we have to cube the scale. If you like, you should know this from maths. So 1,000 centimeters cubed goes into 1 decimeter cubed. So to get from centimeters to decimeters, you have to divide by 1,000, and that's especially important for triple science higher when they like to throw the kitchen sink and more at you. But again, question 7 here, you'll have to do that because you have a measurement in centimeters cubed. Always check the units for these questions. Or they love to throw you in a centimeters cubed and watch you have to convert them. But anyway, the equation, it's quite simple really. Grams per decimeter cubed. Mass divided by volume. Concentration equals mass in grams divided by volume in decimeters cubed. So let's test this out. So 30 grams of salt is dissolved in 40 decimeters cubed of water. So concentration is mass divided by volume. 30 divided by 40. The concentration of salt in the water, 0.75. Once again, I have a bottle of 100 decimeters cubed of dilute hydrochloric acid with a concentration of 0.1 grams per decimeter cubed. So this time we're given the concentration and the volume, so you've got to rearrange the formula so that you can figure out the mass of hydrochloric acid that you have. So obviously if you times both sides by the volume, concentration times volume is going to give you the mass. So we have 10 grams because 100 times 0.1. Make sure you're very good at rearranging the formulas of equations for both for this equation and for our previous moles equals mass over formula mass equation. You're going to need that skill. It is specifically stated many times in the specification that you need that skill, so make sure you're very good at it. For physics as well, and biology actually for that magnification and the other formulas that you might need. We just did this. 1,000 centimeters cubed is 1 decimeter cubed. Really remember that. And then question 7 is a bit harder because you have to convert the units first. So 123.5 milligrams is going to be 0.1235 grams, and 190 centimeters cubed is going to be 0.19 decimeters cubed. And if you put that into the volume, put that into the equation, you do mass divided by volume, and you get the concentration of 0.65 grams to decimeters cubed. Okay, that's everything everyone needs to know about concentration unless you're doing triple science higher, because there is another equation for calculating the concentration of a solution. Concentration equals the moles divided by the volume. So you can do it as mass or you can do it as moles, because obviously moles is also a measure of the amount of a substance. So the units of concentration in this equation would be, as written down here, moles per decimeter cubed, not grams per decimeter cubed, moles per decimeter. Remember, the units basically tell you what the equation is. So, and the equation tells you what the units are. So if you can remember one, then you can easily get the other just from the units. That's very important. So let's have a go. We are told that 0.3 grams of sodium chloride is dissolved in 400 centimeters cubed of water. What is the concentration of sodium chloride in moles per decimeter cubed? So we have to convert mass into moles. How do we do that? Well, we have to bring over the other equations. So moles equals mass divided by the relative formula mass. So our mass is 0.3 grams. Our relative formula mass is 58.5. So we actually have to do 0.3 divided by 58.5, and we have 0.005182 moles, and then remember units, that's going to be 0.4 decimeters cubed of water, isn't it? So if we remember our equation, moles divided by volume, so the 0.005182, keep the number in your calculator, don't round it until the end, and then that divided by the 0.4 decimeters cubed is going to give us a concentration of 0.01828205, and you could probably round that to two or three decimal places. Remember, if it doesn't tell you what to round to, the best thing to do is to look at how far the data is rounded. So if you can see the data like here, rounded to 1 decimal place, then you might want to do that. But obviously in this case, I didn't really take that into account. So, but yeah, good rule of thumb. If you don't know what to round it to the same amount as all the rest of the data is rounded to. So if you see all the data is written to 1 dp, you write your answer to 1 dp. Okay, now here is the very, very hard concentration question. Well, actually, no, I shouldn't say very, very hard. I don't think it's any harder than the limiting reactant question or any of the others. Again, you can see before we've even started, I've constructed the same table I used for all the other questions, apart from because we're dealing with the concentration and the concentration equation. I've constructed the table for the concentration equation, so concentration, volume, and moles instead of mass, formula mass, and moles, and obviously still got molar ratio down here because that's very important. The key to most of the quantitative chemistry questions is the mole ratios and being able to use those to convert the moles and figure out other substances' moles, and then you can go back up. The mole ratio is really the base of a lot of these calculations. But anyway, 50 centimeters cubed of sodium carbonate reacts completely with 60 centimeters cubed of hydrochloric acid with a concentration of 0.31 moles per decimeter cubed. Find the concentration of the sodium carbonate solution used in moles per decimeter cubed. So we have the equation. I haven't put the products because we actually don't need them. So we have the concentration of the hydrochloric acid, and we need to know the concentration of the sodium carbonate solution. So again, we're going to fill in the stuff we have before we do anything else. If I asked you to tell me what was wrong with this so far, because I have made a mistake, have a look. The volume, 60 centimeters cubed, but remember we always have to deal with concentration in decimeters cubed. So 60 centimeters cubed, we need to convert this to decimeters cubed. It's so easy to forget your conversions, and you can just lose so many marks just from simply, you can remember all the really, really hard stuff, but just forget your units and you lose a couple of marks for absolutely no reason. So really, please, 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 please remember your units. So as you can see, I've had to divide by 1,000 because obviously that's our method of conversion from centimeters cubed to decimeters cubed. So then we have everything we need to calculate the amount of moles of hydrochloric acid we actually have here. So if you remember our equation, concentration equals moles divided by volume, we need to rearrange it. So we need to do the concentration times the volume, and that comes out as 0.00186. That's how many moles of hydrochloric acid we have. So we have our mole ratios. We can now work out the amount of moles of sodium carbonate that we have, because remember they react completely, so neither limiting reactants. We kind of have the perfect amounts of both. Look for that react completely, otherwise you might have to consider a limiting reactant or something. So this is going to be 2, but remember in ratio, if this is 1, what do we do from 2 to 1? We halve it, so we have to halve this number, and that comes out to be 0.093. Sorry, I did add an 10 too many into there. So now our only gap, this is our answer, this is what the question asks us for. We have all the data we need now to figure this out. Concentration equals moles divided by volume, 0.093 divided by 0.05, and that comes out to be 1.86 moles per decimeter cubed. That I'm not sure if that can actually be correct, because you can't really have a concentration of more than 1, I don't think. But the process is all correct. That just shows you how to do the process. I thought I'd put all the numbers in beforehand so that you'd get a value less than 1. But there we go. I don't know what happens. So, so they could also ask you then, after you've done all that, what's the concentration in grams per decimeter cubed? Because it's not enough to give it in moles per decimeter cubed. You've got to give it in grams. So how are we going to get from moles per decimeter cubed to grams per decimeter cubed? Well, we've got to change the moles into grams. And how are we going to do that? Well, we have to use our old favourite equation, moles equals mass over formula mass, and rearrange it to get the moles times the relative formula mass gives you the mass. So we're going to have to do 0.93 106, which is the relative formula mass of our sodium carbonate, to give us 9.858 grams. And then we're going to have to divide by the volume again in decimeters cubed. And that gives us an end result of 197.16, probably unrealistically high, 197.16 grams per decimeter cubed, but that illustrates how to do the process. And in the exam, you first of all, you'll know that they'll use correct figures, and second of all, if you do the same process, you're going to get the right answer. Remember the table, our mole ratio, and then the free that the question's asking about, whether it be volume and concentration or whether it be mass and formula mass. You can tell pretty easily. Also, you may have to do this when you do titrations. We're going to cover that in the next video. So if you thought we were done on the calculations, no, we're not. We've still got percentage yield and atom economy to look at, and who wouldn't want to look at those? So the bold questions are only for higher. Pause the video and have a go at these 13. So the yield of a chemical reaction is simply the amount of product that you get. Yeah, that is it. But the catch is, while we calculate that 6.72 grams of nitrogen and 1.44 grams of hydrogen react perfectly to make 8.16 grams of ammonia, the yield, you will never actually get all 100% of the ammonia, or whichever reaction you're doing, you'll never get all 100% out. There's always our maximum theoretical yield, which we calculate through our moles and everything, and then there's the actual yield, which is it's always lower than 100%. That's for 3 reasons. Number 1, there could be side reactions. So, for example, if there are impurities in the chemicals you're reacting, or if some of your reactants react with the air, for example, then they form impurities, and side reactions will happen, and yeah, that will just end up with you not getting. You might get more chemicals than you expect, but you'll end up getting less of the desired chemical than you expect. The second one, which definitely applies to the creation of ammonia through the Haber process, some reactions are reversible, which we look at in paper 2. You don't really need to remember that much for paper 1. All you need to remember is that some reactions, they can happen backwards as well as forwards. You're never going to get 100% of the products, because the products are in fact reacting themselves to go back into reactants. You'll never actually get a 100% yield. The third one is you could, if you need to filter your product to get it, if it's a liquid or a solid, then some of it will get stuck in the filter paper and you will lose that. So your yield is never actually 100%. We calculate percentage yield by dividing the actual yield by the maximum theoretical yield, which you calculate from your moles, or they might give to you. And then obviously you have to times it by 100 to get the percentage, because it's percentage yield as a percentage. So let's try it with question 4. If the maximum theoretical yield of ammonia I can get from a reaction is 60, so there's our theoretical yield, but I only got 45, so there's our actual yield. What is the percentage yield? We're going to do the actual yield divided by the theoretical yield. So 45 divided by 60 comes out to be 0.75, or 75%. Remember, if you get a number greater than 1, you've done them the wrong way round. So you can tell it's 75% yield, because 75% of 60 is 45. That's pretty much what the percentage yield represents. Here's another question. I got 50% of a product from a reaction which had a percentage yield of 72%. What is the maximum theoretical yield I could get? Again, we have to rearrange our formula. Well, first of all, we need to turn our percentage into a decimal, so divide it by 100, 0.72. And if we rearrange our equation, we're going to get the actual yield divided by the percentage yield gives us our theoretical yield. So 56 divided by 0.72 should give us a number larger than 56 grams, and it gives us 77.7 recurring. What a perfect number. There we go. So don't be afraid to have to rearrange the formula. It's not that bad. You should be able to do it from maths. And now two higher questions, which are a bit harder, not too hard, not compared to some of the other stuff we've done. So we have our equation, and we're told that 340 grams of sodium hydroxide, which this reacts completely with 310.25 grams of hydrochloric acid to make this, and what's the maximum theoretical yield of sodium chloride I will get. This isn't really even linked to percentage yield. This is literally just a masses of equations question, so we're going to need to draw out our table. So here's our table with all the bits filled in. You can see our mole ratio is nice and simple, 1 to 1 to 1 to 1. We don't even need to figure out the relative formula mass of both. We can just do it for one and then find the moles for all the others. If you want to pause and have a go right here, then you can. You probably should be able to do this by now. You should find that we have 8.5 moles of each, and what this means is that we also have 8.5 moles of sodium chloride, and this means that after we've worked out the relative formula mass, we can use our equation. We can do these two multiplied together to get the mass, which gives us 497.25 grams of sodium chloride as our maximum theoretical yield. So this might be a percentage yield question. They may tell you the actual yield, ask you to calculate the percentage yield. So if you remember, we do our actual yield of 200 grams divided by our maximum theoretical yield of 497.25 grams, and that gives us a percentage yield of 40.22121 and so on percent. So roughly 40%, if we wanted to round it to the nearest whole number, percentage yield. So here's a challenge question. I'm not going to go through it fully. Have a go and see if you can get the right answer. So we've got our actual yield and our percentage yield, and we need to find the theoretical yield of the product so we can find the amount of reactants. So we're going to rearrange our percentage yield equation. Do 184.96 divided by the percentage yield, but we need to as a decimal, obviously, so 0.8, and that gives us a theoretical yield of 231.2. So now we have our theoretical mass of ammonia, and we can also work out the relative formula mass. We can work out the number of moles. So 231.2 divided by 17 comes out to be 13.6. If you've drawn the ammonia balance symbol equation out, you'll know that the mole ratio is 1 nitrogen to 3 hydrogen to 2 ammonia. We have our number of moles of ammonia, and then we need to find out our multiplier, because obviously it's a ratio. So this times 6.8 gives us 13.6, so we times the others by 16.8. Okay, on to atom economy. It's important not to confuse percentage yield and atom economy. Well, percentage yield refers to the actual yield versus the amount we expect. Atom economy, we're more talking about the useful product versus the total product. So, for example, if we have multiple products but only one of them is useful, what percentage of the total products what percentage mass of the total product is our useful products? That is atom economy. So it's important to have a high atom economy, because obviously if you're producing loads and loads of waste products, then that's bad, isn't it? You don't want loads and loads of waste. That's unsustainable, because we only have a limited number of resources on this world, and if we're wasting loads of them, then there's no point in doing that. And also, it's unprofitable if we aren't producing enough yields to cover the cost of the reactants. Then that's unprofitable. You need a good amount of reactant, you need to make a good amount of the products to have a high atom economy to make a lot of money. That's, so if you remember atom economy, we're talking more about the amount of useful products, and it's more about the economic reasons about atom economy. So we calculate atom economy this time in terms of relative formula mass, because we're actually talking about it on an atomic level. So we do the relative formula mass of the useful products that we want, divided by the relative formula mass of all the reactants that we put in. But you can do relative formula mass of all the products we get out, because they are going to be the same because of our laws of conservation of mass. But we do all reactants because we're talking about the amount we put in versus the useful stuff we get out. You have to times it by 100 and express it as a percentage. So let's have a go. What is the atom economy of the following reaction to produce sodium chloride? So sodium chloride, we are told, is our useful product. So the relative formula mass of our desired product is 58.5 divided by the total relative formula mass of all our reactants, which comes out to be 76.5. So 58.5 divided by 76.5 comes out as 76.47058%. So 76.5%. You could put it as rounded. Okay, a bit harder. Remember, atom economy doesn't get that hard. The atom economy of the photosynthesis reaction to produce glucose being our useful product. So can you remember the balance symbol equation for photosynthesis including glucose? Glucose is C6H12O6, which is 180 in its relative formula mass. And then if we calculate the total relative formula mass of all the products, all of the reactants, but actually it doesn't make a difference, you could do all the products if you wanted to. And all of our reactants have a relative formula mass of 372. So if we do 180 divided by 372, then we find out our atom economy is 48.38709%, or you can round it to 48.4 if you want to. So when in real life we choose chemical reactions to produce specific resources and products, we don't just take into account atom economy. That is one of the things that we take into account. But we also have to take into account our likely percentage yield. If it's, for example, we can calculate it for a reversible reaction like ammonia. We also take into account the rate of reaction, which we look at more in paper 2, especially with the Haber process to make ammonia. The position of equilibrium on reversible reactions, again, we look at more in paper 2. Just remember these as things that we take into account. You don't have to know why and what they are until we get to paper 2. And finally, how useful the byproducts are. So, for example, our byproduct here is water. If we can use the byproducts that we get from the reactions and not just put them in waste, then that might make us want to choose the chemical reaction as well. So there we are. That's all the concentration percentage yield. That's every calculation you need to know. Unless you're triple science higher, and then you have to know yet another final calculation around the volume of gas. And it's centered around this sentence, so try and fill this sentence before you do these questions. Equal amounts of moles of any gas will occupy the same volume if the temperature and the pressure are the same. So what this means is that equal amounts of moles of any gas, so let's take carbon dioxide. If we have 2 moles of carbon dioxide, that will occupy the same volume as 2 moles of oxygen, for example, if the temperature and pressure are the same. Have a go at the other 5. So you need to know the values of room temperature and pressure. Room temperature we consider in this topic in chemistry, we consider room temperature to be 20 degrees C and pressure to be 1 atmosphere. And at room temperature and pressure, our specific room temperature and pressure, 1 mole of any gas occupies 24 decimeters cubed. 24 decimeters cubed. Remember, 24 decimeters cubed. That's a very important number to remember. and we use this to find the equation to calculate the volume of a gas at room temperature and pressure, because we can calculate the number of moles we have of that gas by doing mass divided by relative formula mass using our very, very important chemistry equation, moles equals mass over formula mass. And then, because we have the moles, we then times that by 24, because that's our 1 mole of any gas occupies 24 decimeters cubed. So x moles of any gas is going to occupy 24x decimeters cubed as a volume. So therefore, the volume of gas, mass divided by formula mass to find the moles, and then times by 24 to find the volume of the gas. Let's try it. Calculate the volume of 400 grams of CO2 at room temperature and pressure. So our mass, 400 grams, divided by our relative formula mass of carbon dioxide, which is 44. 400 divided by 44 is 9.09 recurring. And then we have to times that by 24. And that gives us 218.18 recurring. And that's the volume that 400 grams of CO2 will occupy at room temperature and pressure. Now we can also use this to find like the volumes of different reactants and products in chemical equations. So we're going to draw on the Haber process once more. If I carry out the Haber process with 50 decimeters cubed of nitrogen, how much hydrogen will I need to fully react with that nitrogen? So we could, and you may well get a question, I'm not sure. You might have to find, you could find the mass of the nitrogen by first of all dividing by 24 to get the moles of the nitrogen, and then you can draw out your table to find mass and from the relative formula mass. But because we know the mole-to-mole ratio, because we have 1 mole of N2 plus 3 moles of H2 equals 2 moles of NH3. We covered that earlier in the video, didn't we? So we can simply times it by 3, because if we have 1 mole of nitrogen occupying 50 decimeters cubed, remember at the same room temperature and pressure, equal amounts of moles of any gas will occupy the same volume. But if we have 3 times the number of moles of hydrogen than we do nitrogen, then we times this by 3 to get 150. So if nitrogen is 50 decimeters cubed, we will need 150 decimeters cubed of hydrogen. And then, assuming maximum theoretical yield, how much ammonia will I get out? Well, we can do exactly the same thing. Ammonia, we have 2 moles of it, so we can times this by 2. We will, in our maximum theoretical yield in our perfect world, that's never actually going to happen, we would get 100 decimeters cubed. So we really are done now. Apologies if the explanations were quite long. I wanted to make sure everyone fully understood how to do it, because there are a lot of calculations and they can get confusing really quickly because you have to understand the very, very basics. If you don't understand how to calculate relative formula mass back here, none of the other stuff in the video is going to make sense. So practice these questions before the exam. Find some exam questions. It's really easy to go on AQA and scroll through the past papers to find the maths questions. That's what I did here. This was from the November 2020 chemistry paper 1 for on the triple science higher exam. So yeah, also practice the questions. Obviously, come back to the ones you get wrong the next day. That's what I always say. And maybe then the evening before if you want to come back and do them again. Just make sure you have a solid grasp of those calculations, because they're going to come up. You know they're going to come up. So here's the mass, simple mass questions. Then we get onto moles, which are higher tier only. We have the limiting reactant, again, higher tier only. We have the concentration, which was everyone, but then obviously there's some triple science higher only ones as well. And then we have percentage yield and atom economy, where some questions are for higher tier only. And finally, for triple science only, we have the volume of gas. I hope now that you are able to do quantitative chemistry. So many people tell me they can't and that it's really, really hard. But all you really need to understand is that one equation. Remember it, write it on your wall. Moles equals mass divided by relative formula mass. If you can remember that, you're going to smash the maths in your chemistry exam. Please subscribe if you found this helpful. And yeah, I really hope you can smash the maths in your chemistry exam. I know you can with that one formula.